All right. So I think last class I kind of mentioned the final is going to be available kind of Monday. It'll open at 9 o'clock and kind of open all the way through the end of the day on Wednesday. You can get on at any time and take it. Once you start, you'll have 120 minutes or 2 hours to submit it. It's got 2 short answer. I think they both have like 4 or 5 parts to them. So you'll upload your kind of responses to those either with Word, Excel, however you're doing your work, even just a picture of your work you're doing by hand, similar to the other exams. The short answer are worth a little bit more than they were in the previous exams. It's about 40% of the grade, where then 60% of it comes from the multiple choice. I think you'll have that formula sheet that's up there. You should, make sure you have that downloaded, have the tables pulled up. I think that should cover the exams. Are there any questions related to kind of just the structure, like in terms of the structure of the exam, or the other thing kind of similar to the last ones, make sure you're not using Safari, because there's a lot more equations on here that might not show up if you're in that web browser. Other than that, one thing I was going to show you that I think I kind of did at the end of last class, just to be a little bit more, going to go over it again. So I uploaded this Figure Out Your Grade tool. It's just under Files on Canvas. And it's kind of got the different categories for your grade, your first 2 exams. And it doesn't really matter if you flip-flop exam 1 and 2, as long as you get your scores for those first 2 exams entered in here. So you could go to Canvas, look at that Excel category, see what your grade currently is for that. Maybe it's an 80. Your online quiz grade, at this point, since, for the Excel, we still have the 5th Excel and Connect, which still could be completed and turned in by the end of the day today. Once that's done and I get those graded, I'll kind of show you, put up something similar to that I did for the Learn Smart and the online quiz, where I show your grade that's, has the lowest dropped. Well, right now I can't do that for the Excel and the Connect because they haven't all been turned in, right? So if you want to kind of use what your current Connect and Excel grades are, that's what you would kind of put in here. And then once I get those scores that are uploaded that show kind of what your grade would be with the lowest dropped, you can kind of enter those in. So this person had a 90 on the online quiz, 90 on Connect, 100 on Learn Smart. They didn't do very good on the first 2 exams. So you could even play around with, what grade do I need in the final to get whatever desired grade I want. So if I want an 80, if I get an 80 on the final, I'd be really, really close to that cutoff, right? So this person could, maybe, I don't know, get an 83. That's going to round, that's going to be pretty close or round up to that 80. Whereas you could also go in the other direction. What do I need to, not fall below C? Start playing around with this, right? And this is kind of, will give you a pretty good idea of where you're at going into that final, okay? Any other questions for me before we kind of jump into, I'll probably finish up that, I believe we were doing practice exam B, correct? So we could finish up kind of the problems from there. I might do a few problems from practice exam A or answer any questions that people have. So before I jump into, are there any questions, specific questions that someone has on a question or just related to some type of topic, something that's kind of giving you a hard time? No? Okay. So I think we worked through 1 through 4 last class, and then we moved ahead and we kind of worked on this linear regression stuff. So we'll go back and we'll kind of start on problem 5. So problem 5 gives us this idea that the university is changing their policy where they won't charge you for any credit after the 12th credit, right? So as long as you take 12 credits, any credit you take past that point, it's the same cost. So you sample 35 students and find that they increase the number of credit hours they took each semester after this change by about 1.25, right? So we've got this positive increase, or this average difference of 1.25. And then we have a sample variance on that difference of 13.2. So assume that we want to test for whether or not the average difference in the number of credit hours has increased, right? So there we want to know, is that true difference greater than 0? Is a true average difference greater than 0? So that's our alternative hypothesis. We assume the opposite is true. So if we look here at our alternative hypothesis, we have a greater than sign. So we have a greater than or a right-tailed test. So the first question is to calculate the test statistic, right? Well, if we go to our formula sheet, this is one of those where, sometimes I hear people saying it's difficult to figure out which formulas to use. If nothing else, just try to match the notation, right? Here I'm telling you this is a sample difference, and I found a variance for this difference variable. If I go to that formula sheet, okay, I don't have any population variances. I don't have a proportion. This isn't looking at a difference. Hopefully I can kind of match up what I see in that problem with, here's that test statistic. And if I wanted to find a confidence interval, here's the confidence interval equation. It even reminds me, yeah, you should be using that student t distribution, and your degrees of freedom is kind of simply n minus 1. Okay? So here's my test statistic equation. It's really just a matter of plugging those values in. Right? I've got 1.25 is that sample difference. I've got the variance was 13.2, right? And the sample size, 35, right? So it's just a matter of kind of plugging those values into that test statistic. I want to switch this here real quick. All right. So really all I'm doing there, plugging in that 1.25 divided by the square root of, 13.2, and my sample size of 35. Right? Once again, remember, for all these test statistics, well, they all represent the standard deviation of whatever variable we're looking at. Here we're looking at that difference, right? The average difference there. But all our standard deviations in our denominators of our test statistics, here, they all represent standard deviations, so they're always going to be positive, right? So that means the sign of the numerator tells me the sign of the test statistic. So here, I can rule out C right away, right? Because it's negative, and I found a positive difference. From there, it's just a matter of kind of plugging things in and computing this. I thought I had my calculator pulled out. I didn't, so give me 1 second. I'll kind of work these as we're going. So we got what? 1.25 divided by the square root of 13.2 divided by 35. We get about 2.035, right? So this is going to be response D there, okay? So those test statistics really just a matter of kind of plugging those values in. Okay? Now I didn't ask this question, but I could have. So let's say here, well, I wanted to be all in one line, but it's okay. What are the critical values at the 10, 5, and 1% significance levels? All right. So I'm looking for my p-value, my critical values there. Okay, that's the question I'm going to try to answer. Well, I obviously don't have this one written up as a multiple choice response, but what we're thinking about is I've got a right tail test. So what I should be thinking about in terms of my critical values are, well, I'm looking at this student t distribution. I know that it's centered around 0, and I want to find the 3 critical values that give me 0.1, 0.05, and 0.01 kind of in the tails, right? Or in the tail here, because I only have a right tail test. So what's my critical value that gives me 0.1 in that right tail? And my degrees of freedom, simply n minus 1, so 35 minus 1, or 34. So I can use that student t table to look up these values pretty quickly. Right? For right tail test, it's actually pretty easy because those are the values I want. So I'm going to go up here. I've got what? My degrees of freedom of 34, so I'll be looking at this line. The area I want in the tail is 0.1, 0.05, and 0.01, right? Those are my 3 alphas. I got you, hold on. Sorry. The screen to catch up here. All right, so that degrees of freedom of 34, 0.1, 0.05, and 0.01 were the 3 areas we want in the tail. So 1.307, 1.691, 2.441 would be our critical values there. Now, if this was a left-tailed test, I would do this the same way, but it'd be these critical values just negative, right? For a left-tailed test, the critical values are coming from the left side of the distribution, which the left side of the distribution would be negative values, right? Because it would be below 0. Okay? So you could look up critical values here. Now, if I'm making my rejection decision, I already forgot what those values were, so let me go back to see my screen real quick. So 1.307, 1.691, and 2.4 something. All right, so we just kind of wrote those values here. Didn't leave myself a lot of room, but you can kind of remember they correspond to alphas of 0.1, 0.05, and 0.01. So thinking about my rejection decision here, well, if this is the true test statistic, you know, on the exam, I'll probably give you an assumed true test statistic, but here we actually have it, right? That's somewhere in between 1.69 and 2.4. So my test statistic is in the rejection region for the 10 and 5% level, but not the 1%. So I would say that I reject at the 5 and 10% level, right? But not the 1%. I would fail to reject. Okay. Any questions over anything there? Okay, I think the next question, what is it going to ask? It's going to ask about the p-value. So assume that you found this test statistic to be 1.307. At an alpha of 0.05, right? What's my rejection decision and what's the p-value? Well, for right-tailed tests, it'll be the area to the right of 1.307. So if I go to my student t table, I said if I ask you to find a p-value from here, I have to give you one of these exact values. So you go to degrees of freedom 34. Sure enough, 1.307, right? That's our test assumed true test statistic. The area to the right of it is 0.1. So our p-value here is 0.1. Right? I go to my degrees of freedom, find that test statistic. The area to the right is 0.1. Right? Excuse me. So if my p-value is 0.1, the alpha I was given is 0.05, right? My p-value is not less than alpha, right? So if my p-value is not less than alpha, I'll fail to kind of reject it. Actually, oh, it's because I changed the test. Yeah. So I would fail to reject the null here, okay, at that 5% significance level. Now that's because up here we were using the actual test statistic. Down here we were using that assumed true test statistic. Okay. So 0.1 and failing to reject the null, right? Should be our answer there. Okay. Any questions on that one? What if this had been a two-tailed test? What's the only difference there? So let's instead assume, you know, I say here, you know, not using the hypothesis test above, but, you know, a two-tailed hypothesis test, but you still find the same test statistic, then what would my p-value be? So with a two-tailed test, remember, if we found that test statistic of 1.307, and we know the area to the right of it here was 0.1, but if it's a two-tailed test, I could have seen something that was equally as far away from that assumed true difference, but below it, or something even further below it. And all of this now goes against that null, because now if the null is, I forgot what we were looking at, the difference. Now if we're, you know, saying, is it equal to 0? If I see something to the left or right, both goes against the null. So now my p-value would be kind of the total area in the two tails, each tail being the same size. So here my p-value would be 0.2, right? Where I'd multiply this one area I found in the tail by 2. My p-value would be 0.2. The rejection decision still I would fail to reject, but my p-value would be larger if it was a two-tailed test. Okay. Any questions on that one? So, you know, we've got these matched pairs examples that use the student t. We worked through this example where we only had sample variances, and that uses the student t. If we have time here, I'll probably show you one today, even though I have a video already up on YouTube of it, where we'll kind of work through through the other practice exam where I look at the differences in sample proportions. Okay. Okay, but for now, let's do a little bit of linear regression stuff. So I think we kind of talked about question 11, but we didn't do 10 or 12 here. So let's say we want to estimate the relationship between ACT scores and the previous year's athletic department expenses. So this was an example I usually go over in class. We did some other ones. So I probably kind of throw something that looks more similar to some of the questions that we went through, the data sets we worked through. But we can still do this, right? So still want to estimate. So we got ACT scores, our Y variable, and then our X variable is expenses. And we didn't really have an example that looked too much like this, but I'll kind of go through it and hopefully it'll make everything make a little more sense. So we've got, there we go. What we're thinking about is we've got kind of the median ACT score at a university, and that's some function of the expenses on their kind of athletic program. However, the way that this variable is kind of measured is in the $100,000. So a 1 unit increase here would be an increase of $100,000. So we've got 97 universities. We find a slope coefficient, right, of 0.3. So we find that this is 0.3. What would the interpretation of that coefficient be? Well, it's a 1 unit increase in our X variable, which here, that would be $100,000 increase, right? Because that's how we're measuring this, that's the units, would cause the median ACT score of a university to go up by 0.3. So a $100,000 increase in its basketball expenses is correlated with, or, you know, you think about, I shouldn't have said cause, but it's correlated with a 0.3 increase in the median SAT score of the university. Right? That's how we would interpret that. Okay. Now, if I had other variables in this regression, it's the same interpretation. I just add in that phrase, holding everything else in the regression constant. I could have also said, well, how would you interpret the intercept here? So let's say I had also given you, I don't know, the coefficient, the intercept coefficient as well, right? And let's say it's 1.5. Well, remember, kind of the general interpretation of this intercept is if the X variables, in this case, we only have one variable. So if the X variable is equal to 0, the intercept is the predicted value of Y. So here, all right, if expenses equals 0, predicted ACT at a university is that 1.5, right? It's as simple as that for the intercept. Okay. What if I'd asked, so let's say I gave you these two coefficients, and then I asked you, if a team is spending $1 million, what's the predicted ACT, right? Well, if this is measured in hundreds of thousands of dollars, right, then the value that expenses would take on here would actually be what? So $1 million, $100,000 is how this is measured. So this would actually be 10, right? $100,000 goes into $1 million 10 times. Like I said, I'd probably keep this a little, easier on the exam where I don't kind of have the units be, something out of the ordinary. I would have kept them like at the number of dollars, like $1 would be a unit. But if I didn't, this would be kind of the idea. Now that I know that would represent 10, it's easy to make predictions here. 10 times 0.3, right, is 3 plus 1.5, right? I get a prediction of 4.5. Doesn't make a whole lot of, the most sense here, but I'm kind of choosing these numbers just off the top of my head. So, any questions on things like that? So, interpreting slope coefficients, interpreting slope coefficients, intercept coefficients, making predictions are all things I could ask you from just kind of giving you the numbers for a regression that is described to you, which is kind of what I would have been doing here. Okay. We talked about this one last class. If we're thinking about anything for slope coefficients, we said we've always got the following, which is that they're coming from a student t-distribution because we just have this kind of standard error, which we said we can kind of think of as just like the standard deviation of our sample coefficient, if we want to think about it that way. So we're using that student t-distribution, and we're always assuming that those slopes are equal to 0, so we should always have a two-tailed test. That's one thing that we kind of ended last class on. And then often we'll have a question that looks something similar to this on the exam. It's already written, kind of ready to go. Maybe listen or carefully. So assume that a researcher finds they estimate for this men's basketball team expenses coefficient, and they find it's 0.5, right, instead of the 0.3 that I just gave you earlier. If it has a corresponding p-value of 0.003. So the researcher concludes if you spend more money on your basketball program, that will the ACT scores increase in the following year. So what's wrong with this logic? Simply spending more on my basketball program, even though it's correlated with kind of this increase in ACT scores, why would, if I just spend more money, I might not expect ACT scores necessarily increase? Well, this was a very naive regression, right? It's not that this isn't potentially possible. However, we've left off a lot of other important variables, so this slope coefficient will have a bias, right? So we want to make sure, especially when we don't have a very good set of additional control variables here, that we make sure we interpret these slope coefficients as simply a correlation and not causal. So, A, there's nothing wrong with the logic. No, that doesn't imply causation. The results aren't significant. Well, that's actually not the reason, because they're highly significant here. The regression results only provide evidence of a correlation. There may be other, omitted independent variables that are correlated with both the team's basketball expenses and their ACT scores. That's going to be the one that we go with, right? It's just evidence of a correlation. And then the test stat tells us it's significant, therefore the research is correct. Well, it doesn't matter what you find for the test statistic. Second thing you would then check is it significant? But then the third thing you have to remember, there could be other important omitted variables, so that my coefficient is really just evidence of a correlation. Okay? So that one, kind of typically these questions have a pretty similar answer, that this is just evidence of a correlation, not causal. Okay? Any questions on that? Or any of this linear regression stuff? Okay, so that should wrap it up. I think we've worked through every problem on practice exam B there. If we go to the YouTube page, so Professor Lang is here. Playlists, this is section 4. Okay. So we'll scroll down here. Kind of notice I put up, this is me from my other section, basically working through every question just a little bit out of order. So I labeled it in the order in which I go through the problems. But all of practice exam A is in a video that's up on YouTube right now. However, I will work through some of it now unless I have any additional questions, because there's this one I know we haven't kind of seen us work through this. No questions? All right, so we've got this example where we've got 500 men, 500 women. Keeping the sample size the same makes it a little easier to keep track of things. I've got 37% of men on gun, 31% of women. I then tell you that's kind of the group 1 is men, group 2 is women. And I even use the notation that hopefully it should be very easy to match this up to which formulas I need to use. So if I want to build a 90% confidence interval, right, between the gun ownership, if I go to my formula sheet, hopefully I look at this and can see, okay, here's my confidence interval equations. I was given proportions. I'm looking for the difference in proportions. Okay. So here's the guy I want to use. I mean, once I start plugging in the sample proportion values of 0.37 and 0.31, I've got my sample size of 500. The only thing left to do is look up this z-value. Right? So if I'm trying to look up this z-value, remember for confidence intervals, I'm trying to find this z-value such that the area outside my interval is alpha, okay? Well, at the 90% confidence interval, my alpha would be 0.1. that means there's alpha over 2 kind of in each tail or on each side. So 0.1 over 2 is 0.05. And I'm dealing with proportions. So, you know, that confidence interval equation reminds me, but also kind of we laid out kind of last class, I kind of categorized everything for you, that if we're looking at proportions, we should be dealing with that standard normal distribution. So there's two ways I can do this. I could go to my standard normal table and say, okay, look, I know I want 0.05 in that tail. So I'm going to find the closest value. Looks like it's in between these two. So negative 1.64 and negative 1.65. So I use the higher of the two. And then I kind of remember. So it's negative 1.65. But the plus, the positive and negative are already kind of built into that equation for me. You know, thinking about it, I'm wanting to go 1.65 standard deviations above and 1.65 standard deviations below. So kind of those signs, I don't really have to kind of ignore that because it's already built into my equation. You know, once I have that, now I've got everything plugged in. It's just a matter of computation, right? Making sure that I can enter this into my calculator correctly. Now, one thing that might be helpful is to calculate this first. So the square root of all this, calculate that, and then just write that number in here, right? Kind of breaking it down into steps, finding this intermediate value. I think that's usually pretty helpful to kind of prevent you from making some pretty easy just computation errors. The other way that you could have looked up that z value is kind of cheat. I guess it's not necessarily cheat, but you use that student t table, and the area you wanted on each side of the interval was 0.05. If you just scroll down to the very last row, remember, these are your standard normal values. So it'll be a little bit more specific. 1.645 is that z value you would need to get 0.05 in the tail. So kind of you can use that student t table to look up that z value that gives you that alpha over 2 in the tail. Okay. It's going to always be in that last row. So, walking through this too much, we could write this out, just plugging all these values in, but I'm trying to just kind of go through the steps to show you how do you, identify what the equation is. Once we plug all those values we have in, we look up the last thing that we don't know. Now we've just got something we have to enter into our calculator. Okay. And I think if you do that, if I remember right, I think it's 0.011 is your lower bound, 0.109 is your upper bound. So what you could say here, right, with 90% confidence is that kind of male gun ownership is greater than female gun ownership, at least at the 90% level, because 0 is not included here, right? It's only positive values. So you know that difference with 90% confidence is going to be a positive difference, the true population difference, okay? So what if I want to find a test statistic for this example? Once again, I could start, go to my formula sheet. I've got my test statistic equations. Well, I'm dealing with proportions. Hopefully it's pretty easy to identify that, right? So I'll first find P bar by plugging in those sample sizes of 500. I'll then plug in my two sample proportions. Once I have P bar, I'll plug that in, plug in my sample sizes, right? I've been given everything. So this test statistic requires a little bit more work, but it's really, all of these are just, once you kind of identify the correct formula, just getting those values plugged in and getting them plugged in correctly. Now remember, the denominator of our test statistic always represents a standard deviation. So we know this is going to be positive. And because I said I'm only ever going to use assumed true differences of 0, right, for this exam, the numerator really becomes the thing that tells you the sign of your test statistic. If I find a sample difference that's positive, well, positive over a positive is positive. If I find a sample difference that is negative, negative over a positive is negative. So the sign of your numerator tells you the sign of your test statistic, okay? Well, for us, it was what? 0.37 minus 0.31 would be our numerator there. So 0.06, so we should have a positive test statistic. So right away, I can rule out that negative value. I found a sample difference of 0.06, which may not seem very large, but right, the largest difference you could ever find when you're looking at the differences in proportions would be if one proportion is 0 and the other is 1. So the largest difference you can find is 1. So 0.06 isn't that bad. So I'm going to guess that when I'm thinking about the test statistic, and remember, it's a z-value, so it represents the number of standard deviations away from that assumed true value. I think it, this difference of 0.06 is probably more than 0.03 standard deviations away. So I'm thinking B probably doesn't make a lot of sense. If I was guessing here without kind of actually plugging all the values in, I would guess it was either C or D. If we go ahead and plug all those values in, sure enough, you'll get that that calculates to be kind of 2.002. Okay. So I'm not kind of writing these out just for the sake of kind of time and kind of making sure we can go through some other stuff. Because one question I want to add in here too, similar that I did to the last exam, and this is why kind of showing up or watching these even live or watching them after the fact is good. It's getting you prepared for the exam. Is what if I'm looking for the critical values at those same levels that we were earlier? Right? Well, I guess I kind of forgot to kind of really explicitly mention what type of tailed test do we have here. I've got a not equal to sign in that alternative hypothesis, so I have a two-tailed test. So what I'm thinking about is I'm dealing with this standard normal distribution, and for every single alpha value, right? So let's say the alpha of 0.1, I'm actually going to have a pair of critical values that gives me alpha total in the tails, so 0.1 over 2, or alpha over 2 in each tail, right? And then I would have the next one would be the critical value that gives me alpha of 0.05 total in the tails. So what I'm going to end up looking up are the alpha over 2 values, right, for a two-tailed test. So if we think about for my alphas of 0.1, 0.05, and 0.01, alpha over 2 is 0.05, 0.025, 0.005. What I could do is go to my standard normal table, find that 0.05 in the table. We did actually earlier. See, I'll pull it up here. All right, we find 0.005. Okay, that corresponds to a z-value of 1.64, negative 1.65. I could then look up 0.025, 0.005, and get those z-values. Or I can cheat using that student t-table and say, okay, the areas I want in the tail are 0.05, 0.025, and 0.005, right? So I'll kind of use these three columns. And then I'll go all the way down to that very last row, which has a degrees of freedom of infinity, which would represent the normal distribution. So 1.645, 1.96, 2.576. So, well, I got 1.645, 1.96, 2.576. But it's a two-tailed test, so I have pairs of critical values at each alpha, one positive, one negative. Okay. So I think it's probably easiest to look these up on that student t-table in that very last row, but you could use the other method as well. And here's my three critical values. Okay. So if on the short answer I asked you to make your rejection decision here. Well, I want to be able to show you all this, but I want to put it on a new sheet. My cords are getting in the way. All right. So what I just did was fine. So here's my first critical value. So negative 1.645 and 1.645. Negative 1.96, 1.96, 2.576, negative 2.576. Now I'm going to think about my rejection regions, or the areas to the right and to the left. Okay? So that's my kind of setup. The next question is probably going to be something like, so I could have asked you, find the critical values and then here, use this assumed true test statistic of 1.45. What would the p-value and the outcome of the test be? Well, if I was just an open-ended short answer and I just said, what are the critical values? What's the rejection decision with your test statistic? Well, let's assume we found that 1.45. Oh, I didn't want to do that, but here we go. Well, that 1.45 test statistic, if I plot it, would be right here. And it's actually not in any of my rejection regions. Okay? So it's not in any of my rejection regions. You know, and if I left it open-ended, you could use the critical value approach and say, you know, I fail to reject at all, right? Fail at all these levels. Now, if instead you decided that, and I think the multiple choice question that we had asked for the p-value, then it would look something like this, right? So we've got this test statistic of 1.45. The p-value is the probability we saw something that far away from the assumed true difference or something even further. However, for a two-tailed test, we could have seen something that was 1.45 standard deviations below that assumed true value. Remember, this is what we're dealing with. But if I see something below, that could also go against the null. So it would have been as equally as likely for me to see something that far away below the assumed true difference. So I can find this area, but then just have to remember I multiply it by 2. Okay? So if I go to my table and I look up 1.45, that's that z value, that's that test statistic that I gave you. So come down here, 1.45, so 0.9265. So here's a common mistake I'm seeing kind of on the Excels and things like that. So 0.9265. Remember, that's not the area in the right tail. That's you want the area in the right tail. When you look up 1.45 in the table, it's giving you the area to the left. So if you, for some reason, were to look this up and forget, oh yeah, to find the area to the right, I need to subtract that from 1. And you were just to say, okay, that's the area in the tail, I need to multiply it by 2. I'm going to get what, 1.8 something? My p-value is a probability. It can't be greater than 1. So if I do something like this and I'm like, oh, my p-value is 1.8, I know that I made an error. I know I made a mistake somewhere, okay? And the mistake was I had to subtract it from 1 so I can get the area in the right here. This is what, 0.0735. It's 2 tails though, so I need to multiply that by 2, 1.470. So if you ever get something that's above 0, you probably forgot to subtract it from 1 at some point, right? You probably were taking an area, to the left instead of an area to the right. Any questions on kind of that? So my p-value is 0.147. What levels can I reject at? Well, I only reject when, so this should be like burned into your memory, when the p-value is less than alpha. Well, my p-value is 0.147. That's not less than 0.1, not less than 0.05, not less than 0.01. So similar to the critical value approach, I failed to reject it all, right? They should lead us to the same rejection decisions. Okay. So what, that was practice exam B. No, it wasn't. It was practice exam A. All right, so we got 0.147, and I left off the rejection decision here, but if we were trying to make it, we covered that and went through that, okay? We're not gonna have time to work through all of this, but if there's anything that is worth. So just something I wanna reiterate, because I think it's just the easiest points in the exam, and it kills me if anybody ever gets them wrong, is if I give you some regression output, and I asked you to calculate a test, I'm gonna sneeze, excuse me, and I asked you to calculate my test statistic, it's as simple as, and I kind of updated that formula sheet to include that the test statistic for a sample coefficient, just take the coefficient estimate and divide it by the standard error. So here, I kind of have this blocked off on this exam A. You can move this out of the way and you can even recreate and prove to yourself. Actually, right, every single one of these test statistics is just the coefficient divided by the standard error. So 1.2 divided by 0.36 is 3.3, right? And kind of 0.41 divided by 0.14 is 2.9, right? It should be the easiest, just take the coefficient, divide it by the standard error. That gives you your test statistic for that specific slope coefficient, or the slope coefficient associated with that variable. Okay. Another reminder, if on the exam I don't have something like this, and I instead see output that looks like this, right? Always remember that these e's to the negative, these represent moving the decimal point to the left that many times. So these are pretty much 0, okay? Anytime you see e to the negative something, that's essentially a p-value of 0, okay? And I wouldn't ever give you something that's hard, like I wouldn't ask you to calculate the test statistic here, where, 0.002, and then you have to think about, okay, so it's 0.00006, like I'm not gonna make you kind of use a standard error from the table that is e to the negative. Okay. Any questions over anything, any topics, any specific problem or? No? Okay, I think we'll kind of wrap it up. I have a few more comments here, but we've worked through every problem on practice exam B in class. Practice exam A, like I mentioned, we just worked through kind of those middle ones because I think those are important to see me work through. But then the rest of them are up on a video that's up on our YouTube page. We can, so I guess we're gonna meet Monday. I am not gonna have anything prepared, but I will show up here, and if anybody has questions, I'll have the Zoom link open and I'll answer those questions. So I open it up to my other sections that are usually on Tuesday, Thursday as well. So we'll have, anybody who has a last minute question kind of Monday, I'll be available for kind of our regular class hour, but I'm not going to like bring anything. I'm not going to prepare anything. It's just a matter of I'll be available almost like an office hour to ask questions, work through problems. If anybody has questions on problems, I'll work through them and everybody else can see it. But other than that, that's kind of how we'll treat Monday. So, does someone have a question? I thought I heard someone's mic on mute. So, yeah, so that kind of takes us into exam week. If you have any questions as you're studying over the next couple of days, I'll be, checking my email, but on the weekend, getting a response to you immediately may not happen in the first 30 minutes. But early next week, I'll be working. So any questions you have Monday, Tuesday, I should be able to get you very, very quick responses. But I will check my email this weekend and try to get you responses if you do have any questions. Do I drop the lowest? Yeah, so because the due date's set for today, I don't have the Connects and the Excels won't be graded. I'll also try to start working through the Excels as early as possible so I can drop the lowest score and get that reflected and shown on Canvas. But yes, I will be dropping the lowest Connect score and the lowest Excel score. Okay. It might just take until like Monday or Tuesday for that to show up on Canvas to you. Okay. For whatever they don't have a built-in tool where I can do that. So any other questions? Okay, well, like I said, I'll be keeping an eye out for questions coming in via an email. Other than that, kind of good luck studying. I'll be here Monday. If you have any questions or want to see me work through specific problems, I'll have the Zoom kind of up and available for you to log on. Otherwise, thanks for a good semester. Good luck on the exam, and have a good summer break.